You didn't win the Nobel Prize. The team of Bicep that led the Bicep 2 didn't win the Nobel Prize because of some space dust.
That's right. Let's make schmutz.
Which one is the moon? Which one is...
That one's the dust. The space dust, yeah.
What are we looking at? So why is space dust the villain of this whole story?
Well, it's funny, you know, I wrote these books, and I don't know about you, but when you get all these books, I'm sure you get books, people send you books, they always come in these dust jackets, right? I was always like, what the hell is a dust jacket? Like, how much dust is raining down at any moment? I mean, this is immaculate. This room is Russian tidiness galore. But in a normal household, how much dust is raining down? It's not really pretty until I wrote a book. And I realized, you know, I'm writing a story about the origin of the universe, and the prologue, you know, to the cosmos, and dust is going to cover this story. It's actually more a story about astrophysics and cosmology than dust. And this is the link between the cosmological and the astrophysical. So what does that mean? So astrophysics is, broadly speaking, the study of physical phenomena manifest in the heavens, astronomical phenomena. Cosmology is concerned with the origin, evolution, composition of the universe as a whole, but it's not really concerned with stars, galaxies, and planets per se, other than how they might help us measure the Hubble constant, the density of the universe, the neutrino content, et cetera, et cetera. So we have a tendency to kind of look a little bit, you know, they're like, not all astronomers and astrophysicists are equal. They're all equal, but some are more equal than others. So we have kind of a prejudice, a little swagger, right? And cosmologists are studying, you know, we're using Einstein, we're not using like, you know, Boltzmann, or we're thinking of the biggest possible pictures. In so doing, you can actually become blinded to otherwise obvious effects that people, you know, would have not overlooked. In our case, when we sought out the signal, we were using the photons that make up this primordial heat bath that surrounds the universe, luckily only at 3 degrees Kelvin approximately. We're using those as a type of film onto which gravitational waves will reverberate it, make them oscillate preferentially in a polarized way, and then we can use our polarized sunglasses, but in a microwave format, to detect the characteristic twofold symmetry pattern of under rotation. That's the technical way that we undergo it. I mean, there's a lot more to it. But there are more than one thing that can mimic exactly that signal. First of all, when you look at the signal, if inflation took place, big if, but if it took place, the signal would be about 1 or 2 parts per billion of the CMB temperature itself. So a few nanokelvin. The CMB is a few Kelvin. The signal from these B modes would be a few nanokelvin. It's astonishing to think Penzias and Wilson, 1965, measured something that's 1 billion times brighter. And that was what, 60 years ago? Let's call it 60 years ago since they discovered it. Moore's law, you're more expert than that. Let's call it every 2 years. So you're talking about like 2 to the 30th power, doubling or something like that at that. So let's call it 2 to the 20th, something like that. So that's like only 2 to the 10th is 1,000, right? Correct my math, I'm wrong. Yeah, 2 to the 20th is 1 million, right? 2 to the 30th is 1 billion. So we're outpacing Moore's law in terms of the sensitivity of our instruments to detect these feeble signals from the cosmos. And they don't have to deal with, you know, in the semiconductor factory in Santa Clara, California, they don't have to deal with like, you know, meteorites and things like coming into the laboratory. It's a clean room. It's pristine. They can control everything about it, right? We can't control the cosmos. And the cosmos is literally littered with particles of schmutz, of failed planets, asteroids, meteoroids, things that didn't coalesce to make either the Earth, the moon, the planet Jupiter or its moons, or get sucked into them and make craters on them, et cetera, et cetera. The rest of it is falling, and it comes in a power spectrum. There's very few, thank God, Chicxulub-sized, you know, impact or you know, progenitors that will take out all life on Earth. But there's extremely large number of tiny dust particles and microscopic grains, and then there's a fair number of intermediate-sized particles. It turns out this little guy here is the end product of a collapsing star that explodes in what's called a supernova, type 2 supernova. So stars spend most of their life fusing helium nuclei, protons, into and neutrons into helium nuclei, and then from there it can make other things like beryllium and briefly make beryllium and carbon, nitrogen, oxygen, all the way up until it tries to make iron and nickel. Iron and nickel are endothermic. It takes more energy than gets liberated to make an atom of iron. When that happens, there's no longer enough heat supplying pressure to resist the gravitational collapse of the material that was produced earlier. So the star forms, goes inside out. That's how scientists discovered helium was discovered on the sun. I don't know. Did you know? That's why it's called helium. Yeah, they went there at night. And
well done.
They went there at night. No, helium means Helios is the god of the sun. It was discovered in its spectrum from observations of the telescope like 150 years ago. It wasn't discovered like when oxygen and iron was discovered. So it's only a relatively recent comer to the periodic table.
So helium came after oxygen.
Oh no! First hydrogen forms into helium. So that's the first thing that formed.
No, in terms of discoveries.
Oh yeah, after oxygen. Yeah, I think Priestley and others. Dalton discovered it in the 1700s. No, helium was really only discovered from the spectrum of looking at the sun and seeing the weird atomic absorption and called Fraunhofer lines in the solar spectrum. So, but when it tries to make iron, there's no longer any leftover heat. In other words, there's heat left over from fusing, as you know, the son of a plasma physicist. You fuse to hydrogen nuclei, you get excess energy, plus you get helium. So that's why fusion energy could be the energy source of the future, and it always will be. Hopefully it'll come much sooner than that. And so trying to make iron, it takes more energy, doesn't give off enough energy, star collapses, explodes, and what does it spray out into the cosmic interstellar medium? It sprays out the last thing it made, which is that stuff. Luckily for us, because some of that coalesced and made the core of the Earth, onto which the lighter like silica and carbon and the dirt and the crust of the Earth were formed. And some of that made its way to the crust. The iron made its way to the crust. Some of that your mother ate and synthesized hemoglobin molecules. And hemoglobin has iron particles in it. It's a quite amazing substance. Without it, we wouldn't have our red blood. We wouldn't exist as we are.
Is this a very long, complicated mom joke?
I've done enough dad jokes. My quota's up. So taking this object, seriously, there's not all of it gets bound up in a planet. In fact, forming planets is very inefficient. And so there's a lot of schmutz left over, some of which gets in the way of our telescopes looking back to the beginning of time. And some of those molecules, like iron, is used in compass needles, right? They're magnetized. And magnetic fields in our galaxy can align them and make the exact polarization pattern that we're looking for. As if the compass needles get all aligned, that's like the polarization of the dust grain. It's like that polarizing filter. That means light polarized like this will get absorbed, and light polarized like this will go through. Mm-hmm. So it's making 100% polarized light out of an initially unpolarized light source. Mm-hmm. And that's what happened. And what we ended up claiming on March 17th, and I'm sure if you were there, you might remember this, at the Harvard Center for Astrophysics, there was an announcement. There were like 3 or 4 Nobel Prize winners in the audience. And the BICEP 2 team, which I was no longer leading, I was still a member of it. In fact, in the announcement, the first person they mentioned, besides, thank you all for being here, is me and my team at UC San Diego, although I wasn't invited to go to the press conference because that
Harvard
complicated. Yes, exactly. It's a little school up there in Cambridge area. And so they ended up making this announcement that we had discovered the aftershocks of inflation. We had detected the gravitational waves, shaking up the CMB. And on that day, past Lex Fridman podcast, back when it was called Artificial Intelligence, Max Tegmark said, "Goodbye, universe, hello, multiverse, and hello, Nobel Prize." So he saw that as confirmatory evidence, not only of inflation, not only of gravitational waves, but of the multiverse. Goodbye, universe. Hello, multiverse.
Multiverse is a natural consequence
of inflation, yes. According to its prominent, supporters. Yeah.
And of course, leave the poetry to Max, which he does masterfully. Yes. Okay. So the excitement was there. Yeah. I mean, maybe the initial heartbreak for you is there too. Yeah. That's some of the darker moments you're going through, but broadly for the space of science, there's excitement there.
Huge excitement. And I often note that this is a problem in what I call, the science media complex, because oftentimes you'll see things like past guest Sarah Seeger, Venus life, exists. And that will be really, it's fascinating, right? And with the work that she's doing or her colleagues are doing, or Clara, who was on your show as well. And that will be on front page, New York Times, Boston Globe, San Diego Union Tribune. It'll be above the fold, make headlines around the world. And then 6 months, 12 months later, as is the case for us, retraction. Page C17 of the Saturday edition that nobody reads, and underneath the personal. So we have a problem in science that if it explodes, it leads, and we get this huge fanfare. and this is not unique to my experiment. This happened with the earlier discovery of so-called Martian life discovered in Antarctica, which was announced after peer review. We weren't peer reviewed at the point when we made the announcement. We had a press conference, and there are other reasons that the team leaders felt it was important to do that so that we don't get scooped by a referee who's unethical. Yeah. We thought we had done everything right, but that's confirmation bias.
So there's like levels to this.
Yeah, there were many levels. And there were people, me warning about how it would be interpreted and wanting to also make sure that we put all the data out, including the maps, which we still haven't released. And so there were a lot of reasons to be skeptical, but the public never knows this. Yeah. I think so I've made a rule that if I am ever in charge of, doling out large amounts of science funding, that when you should keep kind of an option. In other words, you should have money for publicity. It's fine. Have money for your press conference, but hold in reserve in a bond to be used, hopefully never, but if it's to be used, an equal fund for the retraction, if it should occur.
So you would like to see, because that's a big part of transparency to me, in the space of science, at least, that's as beautiful because it reveals it tells a great story. There's an excitement. There's
humanity.
So there's a climax to the triumph, but there's also a climax to the disappointment at the end, because that also eventually leads to triumph again. That sets up. That's the drama that sets up the triumph. Like with Andrew Wiles, Fermat's last. Fermat's theorem. I guess it's not last name. Whatever. Like the ups and downs of that, the roller coaster, the whole thing should be documented.
That is science. And when we don't do that, then we cultivate this aura that excludes other scientists, often from minorities or women back. That you have to be Einstein. Like Einstein came out of the womb and he was just like this guy with like curly. No, he wasn't. He wasn't bad at math. That's all nonsense. But he said that when he said he attributed his success to, Lex, he said, I never asked my dad what happened when I ran alongside a light beam as a kid. And thank God I didn't, because had I, he would have told me the best answer of the day, which, by the way, he would create 20 years later as a 26-year-old in the patent office, obviously in Switzerland. And in so doing, by delaying when he asked these questions, he said, I approached it with the intellect of a mature scientist, not a little kid. And I wouldn't have accepted the same explanation. So sometimes assuming that scientists are infallible, inevitable, omniscient, I think that really does a disservice. And Jim Gates said, he's like, Einstein wasn't always Einstein. And we cultivate this mystery and allure at our peril because we're humans until we have artificial Einstein, which I don't think will ever exist.